Now, a tunnel boring machine weighing 7,000 tons needs to cross beneath a river carrying 236 million gallons of water every day. The machine cannot surface, the river cannot stop, and the pressure of getting it wrong would flood one of the world's largest cities. London's Thames Tideway Tunnel, often called the Super Sewer, is a 15-mile underground interceptor designed to capture sewage overflows before they reach the River Thames. The system was built because London's Victorian sewers, designed by Joseph Bazalgette in the 1860s, were never intended to serve a population of 9 million people. Every time it rains heavily, untreated sewage spills directly into the river. Roughly 60 times a year, the old system overflows. The new tunnel had to run deep beneath the Thames for most of its length, but at certain points it had to cross directly under the riverbed itself. The Thames at central London is not a static channel, it is tidal, rising and falling by more than 20 feet twice a day. The riverbed consists of layers of gravel, sand, clay, and silt deposited over thousands of years. Beneath that lies the London Clay Formation, a dense blue-grey layer that extends hundreds of feet down. That clay became the target depth for the tunnel. It is stable, predictable, and crucially, it sits below the shifting sediments of the riverbed. But drilling through clay beneath a river introduces an engineering tension. The boring machine operates inside a pressurized chamber. As it advances, it removes material from the tunnel face and simultaneously injects a slurry or foam to support the walls. If the pressure inside that chamber drops too low, water and sediment rush in. If it climbs too high, the slurry breaks through to the surface, or worse, fractures the riverbed from below. The Thames is not deep, averaging only 20 to 30 feet in central London. That means the tunnel boring machine would pass within 60 to 80 feet of the river's surface at key crossings. The margin for error was thin. The first attempt to cross beneath the Thames on this project took place near Chambers Wharf in Bermondsey. Engineers chose a route that kept the machine within the London clay layer for as long as possible. The boring machine, a mixed shield type designed to operate in mixed geology, entered the clay and began its passage. Sensors monitored ground settlement above in real time. Any movement greater than a few millimeters would have triggered an immediate halt. The team controlled the pressure inside the cutting chamber by adjusting the rate at which material was removed and the density of the conditioning agents injected at the face. For 3 weeks, the machine advanced at roughly 30 feet per day. The riverbed above showed no measurable deflection. The turning point came not during a crossing, but in the preparation for one. Before the machine could attempt a second passage beneath the Thames near Blackfriars, engineers conducted a ground investigation that revealed an unexpected lens of water-saturated sand trapped between 2 layers of clay. Sand under pressure behaves differently than clay. It is less cohesive and more prone to sudden movement. If the boring machine encountered that sand lens while pressurized, and if the chamber pressure was even slightly miscalibrated, the sand could flow into the tunnel or blow out toward the riverbed above. The project team decided to inject a grout curtain into the sand lens before the machine arrived. Boreholes were drilled from the surface, and a cement-based mixture was pumped in to solidify the sand. The grouting took 11 days and used more than 200 cubic meters of material. Only after ground samples confirmed the lens had been stabilized did the boring machine proceed. The mechanism that allows a tunnel boring machine to cross beneath a river without disturbing it is called earth pressure balance. The machine's cutting head rotates at the front, breaking up soil and rock. Immediately behind the cutting head is a pressurized chamber filled with excavated material mixed with foam or bentonite slurry. The pressure in that chamber is set to match the pressure of the surrounding ground and groundwater. As material enters the chamber, it is removed at a controlled rate through a screw conveyor. The rate of removal determines the chamber pressure. Remove too much material too quickly, and pressure drops. Remove too little, and pressure rises. The balance must be maintained continuously. On the Thames Tideway project, pressure adjustments were made every few minutes based on sensor data from the tunnel face, the chamber, and the ground surface above. The spoil removed from the tunnel was not waste. It was transported by conveyor to a slurry treatment plant, where clay, sand, and water were separated. The clay was dewatered and loaded onto barges for disposal or reuse. Over the course of the project, more than 5 million tons of excavated material were removed. Much of it came from crossings beneath the Thames. Each barge trip reduced the number of truck movements through London by several hundred, but the logistics of managing that volume added months to the construction timeline and tens of millions of pounds to the cost. Not every river crossing went as planned. During one passage near Carnwath Road, the boring machine stalled for 6 days due to a blockage in the screw conveyor. Excavated clay had compacted inside the conveyor barrel, preventing material from leaving the pressurized chamber. Engineers could not simply reverse the conveyor or flush it with water because that would destabilize the pressure balance at the tunnel face. Instead, they injected a polymer solution into the chamber to liquefy the clay, then slowly restarted the conveyor at reduced speed. The blockage cleared, but the delay meant the machine remained stationary beneath the riverbed for nearly a week. Continuous monitoring confirmed no settlement occurred, but the incident demonstrated how fragile the process was. A blockage in the wrong location or a longer delay could have forced the team to depressurize the chamber and risk a collapse. The cost of crossing beneath the Thames was not evenly distributed. Each crossing required additional grouting, extended monitoring, slower advance rates, and contingency planning that did not apply to tunnel sections beneath solid ground. The Blackfriars crossing alone added an estimated £12 million to the project budget and required 2 months longer than a comparable length of tunnel elsewhere. Multiply that across multiple crossings, and the river became one of the single largest cost drivers on the entire project. The total budget for the Thames Tideway Tunnel exceeded £4 billion, and river crossings accounted for a disproportionate share of both the spending and the schedule risk. Today, the Thames Tideway Tunnel is operational. The boring machines completed their routes, including all crossings beneath the Thames, without a single structural failure or riverbed breach. The tunnel now intercepts sewage overflows from 34 combined sewer outfalls along the river. When the system is fully integrated with London's existing infrastructure, it is expected to capture more than 95% of the overflows that previously entered the Thames. So, the river crossings, once the most uncertain part of the project, are now invisible. 60 feet of clay and water separate the tunnel from the surface, and nothing on the river above suggests what lies below. The lesson is not that the crossings were easy. They were not. The lesson is that the engineering risk was transferred from the river to the preparation. The time spent grouting sand lenses, calibrating pressure sensors, and planning for conveyor blockages determined whether the crossings succeeded. The boring machine itself was a known technology. What made the crossings possible was the decision to treat every meter of riverbed as a distinct geological problem, not a uniform obstacle. London's super sewer crosses beneath the Thames because engineers refused to assume the ground would cooperate. They mapped it, stabilized it, and monitored it in real time. The Thames never stopped flowing, the tunnel never surfaced, and the city above never knew the crossing was happening. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.